Many distributions have similar shapes, but the ones that get used most often for modeling are the ones whose properties make it easy for us to do interesting calculations. Here's an example of how the Poisson is a terrific family to be working with. We'll start with x, a Poisson mu random variable. And now we'll take another one. Y is Poisson with a possibly different parameter lambda. And we'll assume that these two are independent. Let S be their sum. And let's see if we can find the distribution of S. Now, as with any random variable, when you're trying to find its distribution, you start with the possible values. X can be any non-negative integer, Y can be any non-negative integer. So S can be any non-negative integer. So for a generic one of these values, we have to find the chance that the random variable S has this value. Now the random variable S is a function of two random variables, and there's just really only one way to deal with this, which is to see what do those two random variables have to be to make this event happen. So X had to be something. And then Y had to be something else that makes the event happen. And so Y is going to be S minus whatever X is. And these probabilities are going to be ingredients in our calculation. Now X could be 0 and then Y is S, and X could be 1 and then Y is S minus 1. So we have to add up all of those probabilities. It's a great idea to be careful here, so that your subsequent calculation is valid. What's the smallest X can be? It can be 0, and then Y has to be S. And then X can be 1 and Y is slightly smaller, S minus 1 and so on. So what's the largest X can be? That's when Y is at its smallest. And the smallest Y can be 0. So the largest X can be is when Y is 0, X better be S. Now you have the chance of an intersection that you're summing, and happily for us, X and Y are independent random variables. So the chance of that intersection is just the product of the unconditional chances. And this is by independence. Done. The probability is over. What we have to do now is sort out the algebra and see if we get something nice. So plug in the Poisson probabilities. To simplify that sum, there's an awful lot of letters there. It's a great idea to see what the constants are. By constants, and already we have an error. That's not an infinity, that's an S. Constants are the numbers that don't depend on k. Now E is just our universal mathematical constant. Mu is a constant, lambda is a constant. S is a constant. S is the particular value at which you're evaluating the distribution. So let's see what we can pull out of the sum. I think we can pull out an e to the minus mu and an e to the minus lambda, which gives us an e to the minus mu plus lambda that we're pulling out. And I don't think we can pull anything else out. All right, so now we're going to observe. Let's take a look at what we've got here. We've got these factorials. We've got a k factorial and an s minus k factorial. It's just sad that there's not something nice up top. Let's see, we've got a mu to the k and a lambda to the s minus k. Those are just as they are. K is going from 0 to s. And k factorial, s minus k factorial at the bottom is looking awfully like one of those combinatorial terms. If I had an s factorial on the top, that would be very nice. That would be s choose k. But I don't. So the classic thing in math is to do what I just did, which is to put it in, because I want it there, and then take it out again. And now start looking at what you've got outside the sum. You have e to the minus something, and you have an s factorial at the bottom, and that's the chance that your random variable is equal to s. This is looking very Poissonish. So let us examine that sum. We have e to the minus mu plus lambda, 1 over s factorial. Do you recognize that sum? S choose k, mu to the k, lambda to the s minus k, and we're adding that over k goes from 0 to s. That is exactly the binomial expansion of mu plus lambda to the power s. And so what we have ended up with is the chance that our sum is equal to s. That is e to the power minus mu plus lambda to the power s over s factorial. Do you recognize the distribution of capital S? E to the minus something, something to the power, the value divided by the value factorial. That's exactly right. S has the Poisson distribution with parameter mu plus lambda. You've just shown that the sum of two independent Poisson variables is itself Poisson. That the parameter is mu plus lambda makes all kinds of sense. X has Poisson distribution with parameter mu, y is Poisson lambda. So X is going to put a bunch of probability at mu, y is going to put a bunch of probability at lambda. It makes all kinds of sense that S, the sum, should put its probability at mu plus lambda, and we'll have a much more precise way of looking at this very shortly. The main thing to note is that you started out with X, a Poisson variable, y, a Poisson variable, and you added them up. You looked at the sum. And then by partitioning the event capital S equals little s according to what X and Y are, you ended up showing that the distribution of the sum is also Poisson with the parameters that it ought to have.